It would be a little surprising if people with only a passing interest in astronomy thought NASA's latest eye in the sky was called the $10 billion Space Telescope. For a long time, so much focus has been placed on the cost of the James Webb Telescope, so little on the return on investment we will enjoy. But now, James Webb has proved that it is truly worth every penny of its cost. The instruments with outstanding features like never before allow James Webb to make discoveries revealing completely unexpected aspects of our universe that nobody could have predicted. To understand this better, we only need to look to its immediate forerunner, Hubble. In over 30 years of service, the Hubble Space Telescope has revolutionized astronomy. For instance, its images of high redshift supernovae were pivotal in demonstrating that remote supernovae are fainter and therefore more distant than expected. In 1998, this finding contributed to 2011 Nobel Prize in Physics recipients Adam Rees and Brian Schmidt and Saul Perlmutter independently, concluding that the universe's expansion was not happening at a fixed velocity or slowing down, but actually accelerating. This acceleration represents the first direct evidence of a dark energy, a form of energy and pressure expanding space everywhere. Another seminal breakthrough came in 1995 when Bob Williams, then director of the Space Telescope Science Institute, which runs Hubble operations, devoted most of his allotted time on the space telescope to staring at a seemingly dark and empty spot of space for 10 straight days. The resulting Hubble Deep Field image was far from empty. Like a core sample of the cosmos, it was spattered with thousands of galaxies at all ages and stages of development. This image proved to be the final nail in the coffin for the once popular steady-state theory of the universe, showing that the cosmos is not immutable and has in fact changed radically over time. Further deep field images have been taken since, pushing Hubble to the absolute limit of its capabilities to return blurry smudges of light from primitive galaxies as far back as 500 million years after the Big Bang. But to finally understand how the universe went from a dark, gaseous fog of basic elements to the clear, transparent cosmos littered with light we see today, we need to peer even further back in time to first light, when the earliest generation of stars formed in the universe. For that, we need James Webb. The trailblazing telescope is a gold-plated $10 billion machine stuffed with infrared detectors, accented with high-tech lenses, and programmed with ultra-powerful software. Its holy grail device is called the Near-Infrared Camera, or NIRCam, and will lead the charge by collecting a wealth of deep space infrared signals for astronomers to view on the ground. This is why the James Webb is often said to hold the promise of unveiling an unfiltered universe. Looking through the telescope lens instead of a standard optical telescope would be like looking up at the stars from my hypothetical New York dark zone instead of Times Square. There'd be a myriad more sparkles in both cases, even though you're viewing the same sky. It's just that, in our shadowy dark zone analogy, we're viewing extra stars because we're uninhibited by light pollution. On the other hand, the Webb telescope is collecting deep space infrared light and decoding it for us. It will point at the exact same universe that the Hubble has scrutinized for decades and scientists have studied for ages, but it will access luminescence we can't see, possibly revealing concealed spaceborne phenomena like violent black holes, exotic exoplanets, grand spiral galaxies, and maybe even signals of alien life. Its first images have already taken much more than our breath away. In fact, NASA personnel who were the first to lay eyes on the Webb's first light images said they were moved to tears. According to Pam Melroy, NASA's deputy administrator, "What I have seen moved me as a scientist, as an engineer, and as a human being." Only 1 month after the first images were released, the successor to the Hubble telescope revealed new insights on how stars form, galaxies merge, and the early period of the universe. The images are a sight to behold, showing the cosmos in awe-inspiring detail. The discoveries have grown significantly since then, giving scientists a vast treasure trove of data to sift through. After over 2 years in space, having said that the images captured by James Webb are so in-depth that the results have been described as a new age of astronomy. Under the James Webb era, we witness the appearance of a bunch of universe breakers. This term refers to findings that seem to upend established models and theories about the universe's origins and its early evolution. For decades, the prevailing models in cosmology and astrophysics have been constructed on the basis of the Big Bang theory and extensive observations from telescopes like Hubble. These models suggested that, in the immediate aftermath of the Big Bang, galaxies took a long time to form and remained relatively small and disorganized for hundreds of millions of years. However, the images captured by James Webb present a challenge to these long-standing ideas. Its observations reveal galaxies from the early universe that are far more massive and structured than scientists ever thought could exist at such an early stage in cosmic history. Some of these ancient galaxies, existing only a few 100 million years after the Big Bang, display complexities that imply they formed and matured much faster than our models predict. This finding is challenging existing cosmological models and may require scientists to rewrite all the textbook of the beginning of the universe. In particular, these findings made by James Webb are prompting researchers to question the role of dark matter and dark energy in early galaxy formation. Dark matter is believed to act as a gravitational scaffolding for galaxies, helping them to form and grow, while dark energy is thought to drive the accelerated expansion of the universe. However, Webb's observations suggest that galaxies may have formed and matured in ways that are not fully explained by the current understanding of dark matter and dark energy. Another revolutionary aspect of James Webb's observations has been in the realm of star and planet formation. It has captured never-before-seen details of protostellar systems, the cradles where new stars and planets are born. One particularly fascinating target is the famous Orion Nebula, a stellar nursery located about 1,344 light-years away from Earth. Webb's infrared capabilities have provided a clearer view of dense gas clouds and dust that shield protostars and protoplanetary disks from visible light. In these observations, scientists have been able to see the early stages of planet formation in protoplanetary disks, where small dust particles coalesce to form planetesimals, the building blocks of planets. Some of these disks exhibit spiral structures and clumps that indicate the gravitational influences of forming planets, giving us direct insight into the process of planetary formation. Observing this phenomenon in real time is an extraordinary accomplishment, as it provides the first-ever empirical evidence to support theories about planet formation that, until now, have been largely based on simulations and indirect observations. In addition to observing distant galaxies, James Webb has provided unparalleled imagery of star-forming regions within our own galaxy. One of the most remarkable findings is a detailed view of the Carina Nebula's cosmic cliffs, where dense gas and dust clouds are illuminated by young, hot stars. These regions are essential to understanding stellar formation, as they show the early stages of a star's life cycle, from the collapse of gas clouds under gravity to the formation of protostars and eventually main-sequence stars. Webb's observations of these regions have revealed new structures and details about the feedback processes involved in star formation, such as the role of intense ultraviolet radiation from young stars in shaping the surrounding gas clouds. By analyzing the composition and movement of gases in these areas, scientists can study how stars form and evolve, gaining insight into the cycles of star birth and death that drive cosmic evolution. Elsewhere in space, the telescope focuses on dying stars just before they explode in powerful supernovae. Stars on the verge of supernova are fascinating objects. They represent one of the last stages of a massive star's life, after burning through most of its nuclear fuel. James Webb has been able to observe some of these stars at this critical juncture. When these stars finally explode, they send out massive amounts of energy and material, enriching their surrounding regions with heavy elements that become the building blocks of new stars, planets, and eventually, even life. These final moments of massive stars have historically been difficult to study due to their transient nature. But Webb's advanced instruments allow us to capture snapshots that reveal clues about how these stellar GI. Another impressive achievement has been the telescope's detailed imaging of interstellar and intergalactic phenomena. One such phenomenon is the detection of clouds of cosmic dust and smoke-like particles in regions previously thought to be relatively clear. These clouds of cosmic smoke are not only stunning in their own right, but also essential in shaping the evolution of galaxies. Such dust clouds absorb and scatter light, impacting how we observe the cosmos from Earth. This cosmic dust often serves as the raw material from which stars and planets can eventually form, highlighting the telescope's role in illuminating the journey of cosmic materials through space. While this cosmic dust had been known to exist, Webb's sensitivity has allowed astronomers to study it with a clarity that wasn't possible before, revealing the density, structure, and chemical makeup of these clouds. One of James Webb's primary missions is to study exoplanetary atmospheres in the search for habitable worlds. Its infrared capabilities allow it to analyze the atmospheres of planets orbiting other stars by observing the starlight that passes through them during transits. Recently, the Webb Telescope made headlines by revealing new details of the atmosphere of a distant planet, which is about 124 light-years from Earth. Named K218b, this is an interesting exoplanet, a planet that orbits another star. An analysis by a European team of researchers found an abundance of methane and carbon dioxide with very little ammonia, a combination that suggests the world could be a type of oceanic planet, previously only theorized. K218b is located at the correct distance from its star that life is considered possible, and the new analysis suggests another compound, dimethyl sulfide, which is made by life on Earth, may also be in this watery world's atmosphere. Follow-up observations will attempt to determine if the compound is really there, and if it is present, additional work would be needed to rule out possible non-living sources of the gas. Even without life, K218b is helping reveal a whole new class of worlds that are bigger than Earth, but smaller than Neptune. Niku Madhusudan, an astronomer at the University of Cambridge and lead author of the paper announcing the results, previously theorized that such planets could host liquid oceans beneath their atmospheres. He recalls seeing the data that showed the presence of hydrogen and, even more revealing, methane and a lack of ammonia. Research suggests a large planet like K218b could only have that ratio of gases if the atmosphere were interacting with water below. We'd been looking for methane in these low-temperature atmospheres for a decade, and here we found it on the first transit, he says. It was a eureka moment. In 2021, Madhusudan coined the word for these wet planets, Hycean worlds. It sounds romantic, but he just combined hydrogen and ocean in a portmanteau. In addition to being an intriguing type of planet we don't have in the solar system, these worlds are pragmatic to study. They are larger than rocky worlds, making it easier for a space telescope to measure them with remote sensors. The Webb telescope scanned the planet during a pair of 2.5-hour transits in front of its host star in January and April. The onboard instruments scrutinized the starlight passing through the planet's atmosphere, giving astronomers spectral clues that can be used to identify the gases present. Webb, with a cost at the time of launch of $10 billion, is proving its worth to researchers as a tool to examine distant planets. Madhusudan says one 5-hour transit observation with Webb provides more data than 8 combined observations with the Hubble Space Telescope, which would take years to accomplish. It's revolutionary, he says. There are 2 prominent schools of thought in the ranks of those hunting for alien life on exoplanets. Those who expect to find it on a rocky world, like Earth, and those who want to search worlds dominated by oceans. The new study provides tantalizing new clues about possible ocean worlds, and Webb has also turned its gaze to rocky targets. Earlier this year, the telescope observed the nearby Earth-size planets TRAPPIST-1b and the TRAPPIST-1c, revealing that they are probably bare rock without protective atmospheres of CO2, making life unlikely. The findings suggest rocky planets such as these, which orbit a type of cool dwarf star known for giving off flares, may not be suitable environments for living organisms. As Laura Kreidberg of the Max Planck Institute for Astronomy, one of the scientists who studied the TRAPPIST-1 system, said in a statement, "It is extraordinary that we can measure this. There have been questions for decades now about whether rocky planets can keep atmospheres. Webb's ability really brings us into a regime where we can start to compare exoplanet systems to our solar system in a way that we never have before." While the new study strengthens the case for the existence of Hycean worlds, there are still alternative explanations. The same data from Webb can produce slightly different results depending on how the analysis is done, which scientists sometimes refer to as the data analysis pipeline. Folks have already shown that the retrieved abundances from James Webb can be very pipeline-dependent, says Sarah Hurst, a planetary scientist at Johns Hopkins University who specializes in atmospheric chemistry and was not part of the new study. Calculations required to make such a claim are highly sensitive to the amount of various molecules in the atmosphere. Madhusudan agrees that more work needs to be done to confirm the results and says that a team from NASA's Jet Propulsion Laboratory has time reserved to scan the planet with James Webb later this year to gather more data. "This is the start of a long road," he says, "but an exciting one." Water-rich planets like K2-18b are good candidates in the search for alien life. After all, it's the medium that enabled Earth to flourish. But even a planet with a liquid ocean and carbon-rich atmosphere isn't guaranteed to host organisms. It has to be the right size, temperature, and distance from its sun, in what scientists call the habitable zone. K2-18bi orbits a cool dwarf star in the constellation Leo, a place in space that fits all the habitable zone criteria. But the planet's large size, 8.6 times Earth's mass, may work against life. Its icy interior may be wrapped with a thin ocean and atmosphere, so the liquid water may be boiling away into space, possibly thwarting the ambitions of any aspiring life forms. But there is another clue in the Webb data, the possible presence of the molecule dimethyl sulfide. You find DMS in Earth's atmosphere, produced by swarms of phytoplankton in the oceans. As exciting as the possibility of this molecule on another planet is, there is a long way to go before scientists know for sure. It doesn't really seem like there is compelling evidence for DMS in their data, Hurst says. Madhusudan's 6-person team has time reserved early next year to use Webb's mid-infrared instrument, MIRI, a spectrograph that's optimized to detect DMS, to confirm or disprove its presence. "Ask me this time next year," he says of the expected timing of the MIRI results. On Earth, no process is known to create DMS molecules, but oceanic life. However, on a world like K2-18b, the conditions might be right for abiotic, non-living sources. Our understanding of sulfur-bearing chemistry is very Earth and Venus-centric, which are very different atmospheres from a hydrogen-dominated atmosphere like K2-18's, Hurst says. We need many more theoretical calculations and laboratory measurements to understand what the different possible pathways are for creating and destroying DMS in an atmosphere. If DMS is detected on K2-18b, it's time for the theorists to really get involved, Madhusudan says. Their job will be to run countless simulations of the planet's chemistry during its lifespan, trying to detect any possible pathway that would create the signatures James Webb found without the presence of life. Only once, no other explanation is found, can the case for a living ocean on the planet be made. The proof of alien life is often depicted with the discovery of a Martian fossil, the receipt of an interstellar transmission, or even a verified extraterrestrial visitation to the White House lawn. But the actual moment that humanity finds out that we're not alone may be experienced by a solitary data cruncher, seated in front of a computer screen running complex organic chemistry models. Currently, the speed at which the search for life in the universe has increased in just 2 years means a discovery which most felt wouldn't occur in their lifetime may well come within the decade. Of course, Webb's Cycle 3 GO projects also include a wealth of investigations focusing on exoplanets themselves and not just their potential moons. This includes a few that wish to determine whether some exoplanets have the conditions needed to support life as we know it. Among those exoplanet habitability projects is one called Constraining the Atmosphere of the Terrestrial Exoplanet, TOI 4481b. This will use Webb's MIRI for 16 hours to determine if a roughly Jupiter-mass exoplanet, which orbits a star around half as massive as the Sun that sits some 39 light-years away, has been able to hang on to its atmosphere. The result could serve as a first step in understanding the habitability of rocky planets and establishing whether M-type stars, also known as red dwarfs, have terrestrial planets with significant atmospheres. This is important in the search for life beyond Earth, because red dwarfs are the most common stars in the Milky Way. In addition, astronomers widely believe the majority of our universe's large galaxies have supermassive black holes in their hearts, with masses as great as millions or even billions of suns. Some of these supermassive black holes are actively swallowing gas and dust that surrounds them in disks of matter, called accretion disks. These monster black holes' gravitational influences are thought to heat the material in those accretion disks, causing them to emit bright radiation across the electromagnetic spectrum and create regions called active galactic nuclei, AGN. Additionally, any matter that isn't swallowed by the black hole can be channeled to its poles, where it is blasted out as jets of particles traveling at speeds approaching light. When that happens, the phenomenon is called a quasar. The violent conditions of these events make AGNs and quasars the brightest objects in the universe, often luminous enough to outshine the combined light of every star in the galaxies around them. Our theoretical understanding of supermassive black holes has burgeoned since the Event Horizon Telescope, EHT, revealed the first image of a black hole, the supermassive black hole at the heart of the galaxy Messier 87, M87, in 2019. And James Webb's Cycle 3 missions will further contribute to this knowledge. The Cycle 3 supermassive black hole observation programs include the investigation of quasars in the early universe and the nature of the first black holes. Scientists hope to understand how those black holes may have influenced the growth of galaxies over billions of years. Webb's observations of supermassive black holes in the early universe could also reveal how these cosmic titans grew to the tremendous masses scientists observe before the universe was even 1 billion years old. Such a question can be answered by using MIRI to investigate if a giant molecular cloud that existed around 13.2 billion years ago could have directly collapsed, birthing a heavy black hole seed that would account for a rapid growth mechanism. On the other hand, one of the primary roles of the James Webb Telescope is investigating objects in the early universe. The powerful space telescope has this capacity because the expansion of the universe stretches wavelengths of light from distant objects as this light travels toward us, moving the wavelengths toward the red end of the electromagnetic spectrum. The longer that light has traveled to reach us, the more red-shifted the light has become. This means light that has been traveling for around 12 billion years is extremely red-shifted, all the way into the infrared region of the electromagnetic spectrum and outside the visible range we can see with the unaided eye. Effectively, infrared light is invisible to us. However, the observatory is capable of observing this infrared light and thus helps to investigate the first stars and earliest galaxies, something it will continue to do in 2025 with several Cycle 3 GEO projects. That's why cosmologists are particularly enthusiastic about GO projects that will look at an era of cosmic evolution called the Epoch of Rionization, which occurred around 500 million years after the Big Bang. During this period, neutral atoms of hydrogen populating the cosmos were ionized by radiation that stripped away their electrons and left them as ionized hydrogen, or hydrogen ions. Studying high redshift galaxies can reveal more about this crucial stage in cosmic evolution, including how the first galaxies acted as the source of this ionizing radiation. Some of the proposals that catch their interest are understanding galaxy formation at cosmic dawn, galactic winds in the early universe, and dead or alive, unveiling the nature of massive galaxies in the early universe. All of these accepted projects seek to identify and characterize galaxies that are the drivers of the epoch of Rionization. Of course, this is just the tip of the celestial iceberg when it comes to the range of topics Cycle 3 GO projects will cover. Between 2024 and 2025, astronomers will also train telescopes on distant stars to better understand stellar physics and populations, as well as examine the gas that exists between stars that can become the building blocks of the next generation of stars and planets. And though the Webb Telescope was designed with the study of distant objects in mind, Cycle 3 will also see the observatory used to study bodies within our own solar system. These will include hunting for the source of gas plumes coming from Saturn's moon Enceladus, investigating the dynamics of the Uranus's rings, and characterizing icy objects that exist in the Kuiper belt at the very edge of the solar system. Looking beyond James Webb Cycle 3, the call for Cycle 4 GO proposals will go out on August 1, 2024, with a deadline set for October 16 this year. The Cycle 4 Telescope Allocation Committee review will run between February 3 and February 12, 2025, with selections revealed around March 5 next year. Webb's Cycle 4 GO programs will then begin making observations of the cosmos on July 1, 2025. Where such jets are fast, in the inner regions of a galaxy, they drive away gas and snuff out star formation. Where they have slowed, in the outer regions, they compress gas and trigger star formation. In fact, powerful jets from the biggest holes seem to control the masses of stars that form, with a tendency towards smaller, cooler stars like our Sun. So, who knows? It might be the case that we can thank Sagittarius AA for our Sun, without which you probably wouldn't be reading this page. 3. What is dark matter? Dark matter gives out no light or too little light for us to detect. We know it exists because we see the effect of its gravity on the visible stars and galaxies. For instance, the Milky Way could not have dragged in enough matter to make its stars in the 1382 billion years since the Big Bang without there being a lot of invisible matter whose extra gravity speeded things up. The European Space Agency's Planck satellite found that dark matter accounts for 26.8% of the mass energy of the universe, compared with the 4.5% of normal atomic matter. It therefore outweighs the visible stars and galaxies by a factor of about 6. For a long time, the favored candidates for dark matter particles have been weakly interacting massive particles, or WIMPs. But although these particles fit the bill, they have failed to appear at the Large Hadron Collider near Geneva in Switzerland. A candidate gaining favor is the superlight Axion, a hypothetical subatomic particle. A rank outsider remains primordial black holes left over from the Big Bang. Puzzlingly, no Earth-based experiment has found any evidence of dark matter despite decades of searching. It is conceivable that it is not our theory of matter that needs modification, but our theory of gravity, or that dark matter is not a fluid made of a single particle, but is complex like the atomic matter we see around us. Maybe the universe is filled with dark stars and dark planets and dark life. 4. Does time exist? Time is what stops everything happening at once, said American physicist John Wheeler. But time is a slippery concept. Most of what we think we know is false. For instance, we imagine time flowing. However, for something to flow, it must flow with respect to something else, just as a river flows with respect to a riverbank. So, does time flow with respect to something else? A second type of time? The idea seems nonsensical. Most likely, the flow of time is an illusion created by our brains to organize the information constantly flooding in through our senses. We also have a strong sense of a shared past, present, and future. However, the idea of a common present appears nowhere in our fundamental description of reality: relativity. Precisely how someone else's time is sliced up depends on how fast they are moving relative to you or the strength of the gravity they are experiencing. These effects are noticeable only at relative speeds close to that of light or in ultra-strong gravity, which is why they are not obvious in the everyday world. Nevertheless, they lead to the idea that one person's interval of time is not the same as another person's, and that one person's interval of space is not the same as another's. Actually, it is worse. Space and time are inextricably intertwined. In our universe, all events, from the Big Bang to the death of the universe, are laid out in a pre-existing four-dimensional space-time map. Nothing actually moves through time. As Einstein wrote after the death of his friend Michel Besso, "Now he has departed from this strange world a little ahead of me." That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. If the expansion of the universe is imagined running backwards like a movie in reverse, in its earliest moments space and time are both ripped apart. Physicists therefore suspect that in the Big Bang time emerged from something more fundamental. As yet, no one knows what that might be. 5. What is dark energy? It's invisible, fills all of space, and its repulsive gravity is speeding up the expansion of the universe. Dark energy was discovered by astrophysicists in 1998. They were studying Type 1a supernovae, stellar explosions believed to unleash a fixed amount of energy and burn with a standard luminosity like a cosmic 100W light bulb. The problem was that the most distant supernovae were fainter than expected. Cosmic expansion had speeded up, pushing them further away. At the time, the only force thought to be operating in the large-scale universe was gravity, which acts like an invisible web between the galaxies, breaking cosmic expansion. The discovery that the expansion of space was speeding up gobsmacked cosmologists who were forced to postulate the existence of a substance that accounts for an astonishing 2/3 of the mass energy of the universe. This dark energy overwhelmed gravity and gained control of the universe about 5 billion years ago. One possibility is that dark energy is a cosmological constant, an intrinsic repulsion of space. Such repulsion might arise from quantum energy fluctuations in the vacuum. However, when quantum theory, our best theory of the submicroscopic world, is applied to the vacuum, theorists predict an energy density that is 10, followed by 120 zeros, bigger than that of the dark energy. The biggest discrepancy between a prediction and an observation in the history of science. Conceivably, the discrepancy will disappear when we finally manage to combine quantum theory with Einstein's theory of gravity. Meanwhile, space experiments may help, one of which is dark matter hunter Euclid, which launched into space in 2023. According to scientists, this telescope is designed to measure how dark energy varies with cosmic time, hopefully providing a vital clue to solving what is the biggest puzzle in science. 6. Why have we seen no sign of aliens? In 1950, Enrico Fermi, the man who built the first nuclear reactor, was having lunch in the canteen of the Los Alamos bomb lab in New Mexico when he suddenly said, "Where is everybody?" Everyone around the table knew exactly what he meant. Decades later, Fermi's question was examined independently by the American physicists Michael Hart and Frank Tipler. Hart considered aliens spreading throughout our Milky Way, and Tipler considered self-replicating machines that, on arrival at a planetary system, exploit the resources to build two copies of themselves that continue voyaging. Both concluded that, even at modest speeds of travel, every star in the galaxy would be visited in a fraction of the age of the Milky Way. As Fermi realized, the aliens should be here on Earth. They do not appear to be. This became the Fermi paradox. Hundreds of explanations have been proposed, but consensus has so far failed to materialize. Thus, it remains a puzzle. But that's understandable. As Douglas Adams observed so perceptively in The Hitchhiker's Guide to the Galaxy, space is big. You just won't believe how vastly, hugely, mind-bogglingly big it is.
The Webb looks so far out that it's capturing light that's been travelling for over 13 billion years. But the universe has been expanding, and so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang.
The universe has not existed forever. It was born. Around 1382 billion years ago, matter, energy, space, and time erupted into being in a fireball called the Big Bang. It expanded, and from the cooling debris, there congealed galaxies, islands of stars of which our Milky Way is one among about 2 trillion. This is the Big Bang theory. But the universe popping into existence out of nothing is so bonkers that scientists had to be dragged kicking and screaming to the idea. Even the physicist Brian Cox also said he strongly suspected that the universe existed before the Big Bang, throwing the theory of our origins on its head.
A cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again.
Things got worse as James Webb, the most powerful space telescope, obtained some very strong evidence demonstrating that the Big Bang wasn't truly the start of it all. All begs the question, what happened before the Big Bang? And if the Big Bang wasn't the beginning, what was it? Join us as we shed some light on the origin of the universe. The first time the phrase the Big Bang was uttered was over 20 years after the idea was first described. Ironically, the term itself comes from one of the theory's greatest detractors, Fred Hoyle, who was a staunch advocate of the rival idea of a steady-state cosmology. In 1949, he appeared on BBC Radio and advocated for what he called the perfect cosmological principle, the notion that the universe was homogeneous in both space and time, meaning that any observer not only anywhere but anywhen would perceive the universe to be in the same cosmic state. He went on to deride the opposing notion as a hypothesis that all matter of the universe was created in one Big Bang at a particular time in the remote past, which he then called irrational and claimed to be outside science. But the idea, in its original form, wasn't simply that all of the universe's matter was created in one moment in the finite past. That notion, derided by Hoyle, had already evolved from its original meaning. Originally, the idea was that the universe itself, not just the matter within it, had emerged from a state of non-being in the finite past. And that idea, as wild as it sounds, was an inevitable but difficult to accept consequence of the new theory of gravity put forth by Einstein back in 1915, general relativity. When Einstein first cooked up the general theory of relativity, our conception of gravity forever shifted from the prevailing notion of Newtonian gravity. Under Newton's laws, the way that gravitation worked was that any and all masses in the universe exerted a force on one another, instantaneously across space, in direct proportion to the product of their masses, and inversely proportional to the square of the distance between them. But in the aftermath of his discovery of special relativity, Einstein and many others quickly recognized that there was no such thing as a universally applicable definition of what distance was, or even what instantaneously meant with respect to two different locations. With the introduction of Einsteinian relativity, the notion that observers in different frames of reference would all have their own unique, equally valid perspectives on what distances between objects were and how the passage of time worked. It was only almost immediate that the previously absolute concepts of space and time were woven together into a single fabric, space-time. All objects in the universe moved through this fabric, and the task for a novel theory of gravity would be to explain how not just masses, but all forms of energy shaped this fabric that underpinned the universe itself. Although the laws that governed how gravitation worked in our universe were put forth in 1915, the critical information about how our universe was structured had not yet come in. While some astronomers favored the notion that many objects in the sky were actually island universes that were located well outside the Milky Way galaxy, most astronomers at the time thought that the Milky Way galaxy represented the full extent of the universe. Einstein sided with this latter view, and, thinking the universe was static and eternal, added a special type of fudge factor into his equations, a cosmological constant. Although it was mathematically permissible to make this addition, the reason Einstein did so was because without one, the laws of general relativity would ensure that a universe that was uniformly distributed with matter, which ours seemed to be, would be unstable against gravitational collapse. In fact, it was very easy to demonstrate that any initially uniform distribution of motionless matter, regardless of shape or size, would inevitably collapse into a singular state under its own gravitational pull. By introducing this extra term of a cosmological constant, Einstein could tune it so that it would balance out the inward pull of gravity by proverbially pushing the universe out with an equal and opposing action. But two developments, one theoretical and one observational, would quickly change this early story that Einstein and others had told themselves. In the 1920s, Belgian physicist and Catholic priest Georges Lemaitre proposed a revolutionary idea, that the universe began as a primeval atom, which then expanded to form everything in existence. In 1927, Lemaitre published a paper proposing that the universe was expanding, a theory he based on Einstein's general relativity equations. Although his work initially received little attention, it became one of the key foundations for the Big Bang theory. Lemaitre's insights suggested a universe that had a specific starting point in time, radically challenging the static universe model. Around the same time, American astronomer Edwin Hubble made a groundbreaking discovery at the Mount Wilson Observatory in California. Observing distant galaxies, he noted a redshift in their light, meaning that the wavelengths of light from these galaxies were stretched, indicating that they were moving away from Earth. Hubble's work provided empirical evidence for the expansion of the universe, bolstering Lemaitre's theoretical predictions. In 1929, Hubble's law emerged, establishing a linear relationship between the distance of a galaxy and its velocity of recession, a key component supporting the Big Bang model. Fast forward to the 1960s and 1970s, as well as ever since, a combination of observational and theoretical advances unequivocally demonstrated the success of the Big Bang in describing our universe and predicting its properties. The discovery of the cosmic microwave background and the subsequent measurement of its temperature and the black body nature of its spectrum eliminated alternative theories like the steady-state model. The measured abundances of the light elements throughout the universe verified the predictions of Big Bang nucleosynthesis, while also demonstrating the need for fusion in stars to provide the heavy elements in our cosmos. And the farther away we look in space, the less grown-up and evolved galaxies and stellar populations appear to be, while the largest scale structures like galaxy groups and clusters are less rich and abundant the farther back we look. The Big Bang, as verified by our observations, accurately and precisely describes the emergence of our universe as we see it, from a hot, dense, almost perfectly uniform early stage. But what about the beginning of time? What about the original idea of a singularity and an arbitrarily hot, dense state from which space and time themselves could have first emerged? That's a different conversation today than it was back in the 1970s and earlier. Back then, we knew that we could extrapolate the hot Big Bang back in time, back to the first fraction of a second of the observable universe's history. Between what we could learn from particle colliders and what we could observe in the deepest depths of space, we had lots of evidence that this picture accurately described our universe. But at the absolute earliest times, this picture breaks down. There was a new idea, proposed and developed in the 1980s, known as cosmological inflation, that made a slew of predictions that contrasted with those that arose from the idea of a singularity at the start of the hot Big Bang. In particular, inflation predicted a curvature for the universe that was indistinguishable from flat to the level of between 99.99% and 99.9999%. Comparably, a singularly hot universe made no prediction at all. Equal temperatures and properties for the universe, even in causally disconnected regions. A universe with a singular beginning made no such prediction. A universe devoid of exotic high-energy relics like magnetic monopoles. An arbitrarily hot universe would possess them. A universe seeded with small magnitude fluctuations that were almost, but not perfectly, scale invariant. A non-inflationary universe produces large magnitude fluctuations that conflict with observations. A universe where 100% of the fluctuations are adiabatic and 0% are isocurvature. A non-inflationary universe has no preference. A universe with fluctuations on scales larger than the cosmic horizon. A universe originating solely from a hot Big Bang cannot have them. And a universe that reached a finite maximum temperature that's well below the Planck scale, as opposed to one whose maximum temperature reached all the way up to that energy scale. The first three were post-dictions of inflation. The latter four were predictions that had not yet been observed when they were made. On all of these accounts, the inflationary picture has succeeded in ways that the hot Big Bang, without inflation, has not. During inflation, the universe must have been devoid of matter and radiation and instead contained some sort of energy, whether inherent to space or as part of a field, that didn't dilute as the universe expanded. This means that inflationary expansion, unlike matter and radiation, didn't follow a power law that leads back to a singularity, but rather is exponential in character. One of the fascinating aspects about this is that something that increases exponentially, even if you extrapolate it back to arbitrarily early times, even to a time where TE, it never reaches a singular beginning. Now, there are many reasons to believe that the inflationary state wasn't one that was eternal to the past, that there might have been a pre-inflationary state that gave rise to inflation, and that, whatever that pre-inflationary state was, perhaps it did have a beginning. There are theorems that have been proven and loopholes discovered to those theorems, some of which have been closed and some of which remain open, and this remains an active and exciting area of research. But one thing is for certain, whether there was a singular ultimate beginning to all of existence or not, it no longer has anything to do with the hot Big Bang that describes our universe. From the moment that inflation ended, the hot Big Bang occurred. The universe became filled with matter and radiation and more, and it began expanding, cooling, and gravitating, eventually leading to the present day. There are still a minority of astronomers, astrophysicists, and cosmologists who use the Big Bang to refer to this theorized beginning and emergence of time and space. But not only is that not a foregone conclusion anymore, but it doesn't have anything to do with the hot Big Bang that gave rise to our universe. The original definition of the Big Bang has now changed, just as our understanding of the universe has changed. If you're still behind, that's okay. The best time to catch up is always right now. Because James Webb, the supreme observatory that was built to revolutionize our understanding of the universe, is providing more and more evidence that the Big Bang wasn't really the beginning of it all. Stationed 1.5 million kilometers away from earthly interference and chilled close to absolute zero by its tennis court-sized sunshade, the telescope's giant segmented mirror and exquisitely sensitive instruments were designed to uncover details of cosmic dawn never before observed. Since it first started sending back science data in mid-2022, the internationally funded state-of-the-art telescope has been giving us images of distant galaxies that appear to have formed and matured far earlier than our models predicted. Webb's Hall of Galactic Baby Pictures has proved more bountiful than most researchers dared to dream. Simply put, Candidate galaxies in the early universe are popping up in numbers that defy predictions, with the dozens found so far. It's enough of a problem that some are calling it a challenge to our entire cosmic timeline. According to the standard model of cosmology, after the fiery Big Bang 13.8 billion years ago, the universe cooled, and energy turned into matter that eventually coalesced during the first few 100 million years, forming the first generation of stars and galaxies. Astronomers thought they had a decent understanding of this process. But Webb's results may suggest that stars and galaxies were forming far faster than anyone expected. The telescope had done nothing less, read the headlines then, break the universe, and upend models of cosmic history. Subsequent data have ruled out some of the more dramatic findings, and new simulations can accommodate at least a few of the strange observations. But some bright, massive, and early galaxies continue to confound theorists, suggesting that our understanding could shift in the coming years. According to Priyamvada Natarajan, a theoretical astrophysicist at Yale University in New Haven, Connecticut, no data at the moment has broken the universe, but I think there are interesting potential tensions emerging on different scales. Resolving these tensions will require researchers to revisit their fundamental assumptions about galactic evolution. That could mean bringing new ideas to the forefront, while leaving others in the cosmic dustbin. Prior to the launch of James Webb, no one knew if galaxies could even form so early in the universe's 13.8 billion year history, at a time when matter was thought to still be sedately coalescing into the gravitationally bound clumps required to give birth to large groups of stars. As Garth Illingworth, an astronomer at the University of California, Santa Cruz, said at a press conference held by NASA to announce the peer-reviewed validation of the first two candidates. And so we're wondering, do we really understand the early phases of the formation of these galaxies? This has posed a lot of questions for the theorists. Chief among them is how exactly dark matter guided the emergence of galaxies. For the first few 100,000 years after the Big Bang, the cosmos was so hot that gravity could not pull normal matter together to form large protogalactic clumps. But this was not an issue for dark matter, says Jorge Peñarrubia, a cosmologist at the University of Edinburgh in Scotland, because dark matter does not interact via electromagnetic forces. Instead, gravity alone is this invisible substance's master, meaning that in mere moments after the Big Bang, when primordial chaos otherwise reigned, gravity immediately began glomming together dark matter into large clumps known as halos. These dark matter halos are believed to have acted as gravitational sinks for normal matter, seeding the subsequent formation of galaxies in the early universe. The telltale motions of the stars they shepherd betray their endurance to this day. Such halos still surround galaxies like our own, majestic but invisible sculptors of the modern cosmos. James Webb's rapid discovery of early galaxies might be testing our understanding of how these halos form, perhaps suggesting they reached an immense bulk earlier than expected. One explanation might involve the very nature of dark matter itself. Theorists have found that simple treatments of dark matter, in which it only interacts with itself and normal matter via gravity, can accurately replicate large-scale cosmic structure. But nature has no guarantee of simplicity. In reality, dark matter could interact with itself because of an as-yet unknown force, perhaps via a particle that's not in the current standard model of physics, possibly increasing the speed at which these halos grew and explaining how big, bright galaxies were able to arise so quickly. However, perhaps instead these halos were simply more efficient at drawing in regular matter to feed star formation. Today our galaxy produces roughly one new star per year, but Castellano's paper suggests that star formation rates must have been at least 20 times higher in his and Naidu's two candidate galaxies. Another Webb-derived preprint paper posits that Milky Way-sized galaxies could have arisen just at 500 million years after the Big Bang, a scenario that would demand star formation rates 10 times higher still than Castellano's estimates. But according to Michael Boylan Colchin, a cosmologist at the University of Texas at Austin, such outsized rates of star formation stretch the boundaries of what is physically possible. In the words of Boylan Colchin, if those values are correct, you'd need to have our galaxies turning all their mass into stars and forming stars as fast as they could. Researchers have likened the impossible early galaxy problem to flipping through someone's old photo album, expecting to find baby pictures, and seeing a full-grown adult instead. With a person, you might just conclude that they're older than you thought, but with early galaxies, you very quickly run into a problem with the age of the universe itself. For generations, people argued over whether the universe had always existed, whether it had a beginning, or whether it was cyclical, with neither a beginning nor an end. But starting in the 20th and continuing into the 21st century, we not only drew a scientific conclusion to that question, the universe, as we recognize it, began with a hot Big Bang, but we were able to pinpoint precisely when that beginning occurred. The simplest and most straightforward way to measure the age of the universe is simply to look at the objects that are in it. Stars, for instance. We have hundreds of billions of stars in the Milky Way galaxy alone, and the overwhelming majority of the ancient history of astronomy was devoted to studying and characterizing stars. It remains an active field of research today, as astronomers have uncovered the relationship between observed properties of stellar populations and how old they are. The basic picture is that a cloud of cold gas collapses under its own gravity, leading to the formation of large numbers of new stars all at once that come in all different masses, colors, and brightnesses, and the largest, bluest, brightest stars burn through their fuel first. Therefore, when we look at a population of stars, we can tell how old it is by looking at what types stars still remain and what classes of stars are completely gone. Our galaxy has stars of all different ages in it, but the measurements of any individual star will be riddled with uncertainties. The reason is simple. When we view an individual star, we see it as it is today. We cannot see or know what happened in that star's past history that may have led to its present condition. We can only view a present-day snapshot of what exists and have to infer the rest. You'll often see attempts made to measure the age of an individual star, but that always comes along with an assumption that the star didn't have an interaction, merger, or other violent event in its past. Because of that possibility, and the fact that we only see the survivors when we look at the universe today, those ages always come along with massive uncertainties, on the order of 1 billion years or even more. However, the uncertainties are much smaller when we look at large collections of stars. The collections of stars that form within a galaxy like the Milky Way, open star clusters, typically contain a few thousand stars and only last a few 100 million years. The gravitational interactions between these stars eventually cause them to fly apart. While a small percentage last 1 billion years or even a few billion years, we have no known open star clusters that are even as old as our own solar system. However, globular clusters are larger, more massive, and more isolated, found throughout the halo of the Milky Way and most large galaxies. When we observe them, we can measure the colors and brightnesses of many of the stars inside, enabling us, so long as we understand how stars work and evolve, to determine the ages of these star clusters. Although there are uncertainties here as well, there is a large population of globular clusters, even within the Milky Way alone, with ages of 12 billion years or more. How certain are we of these figures? It's tough to say. While it's almost guaranteed that the oldest of these star clusters must be between 12.5 and 13 billion years old, there remain large uncertainties about the amount of time required for a star right around the mass of our Sun to begin its transition into a subgiant, followed by its transformation into a full-blown red giant star. It could be 10 billion years, it could be 12 billion years, it could be some value in between. For years, many astronomers who worked on globular clusters argued that the oldest ones were 14, maybe even 16 billion years old. But a shift in our understanding of stellar evolution now disfavors that interpretation of the data. Today, we can reliably conclude there's a lower limit to the age of the universe of around 12.5 to 13 billion years from the stars we measure. But that doesn't pin down the age precisely. It's a good constraint to have, but to arrive at an actual figure, we'd like a better method. Fortunately, the universe gives us one. You see, Einstein's general relativity, for a universe filled with even amounts of matter and energy everywhere and in all directions, gives a straightforward relationship between two quantities: the amounts and types of matter and energy present within the universe, and how fast the universe is expanding today. This relationship was first derived all the way back in 1922 by Alexander Friedmann, and the equations that enable us to derive how old the universe must be are known as the Friedmann equations. It took us many years to measure the constituents of the universe, but a consensus picture has emerged. Observations ranging from the abundances of the light elements to the clustering of galaxies, to how galaxy clusters collide, to distant supernovae, to the fluctuations in the cosmic microwave background, all point toward the same universe. In particular, it's made up of 68% dark energy, 27% dark matter, 4.9% normal matter, 0.1% neutrinos, 0.01% photons, and less than 0.4% of everything else, including spatial curvature, cosmic strings, domain walls, and other fanciful, exotic components. This picture agrees with the full suite of observations that we have. You have to really cherry-pick your evidence very hard, overemphasizing measurements with large ambiguities while simultaneously ignoring large suites of data, to wind up with sets of values that vary significantly from this. So then, you might think that everything hinges on the expansion rate. If you can accurately measure that, you can simply do the math and precisely arrive at the age of the universe. Beginning the early 2000s and ever since, the best data we have comes from the cosmic microwave background, first from WMAP, then from Planck, and as of July 14, 2020, from the Atacama Cosmology Telescope as well. Those values have all converged on the same expansion rate, 68 kilometers SSMPC, with an uncertainty of just 1 to 2%. When you calculate what that means for the age of the universe, you get a very robust 13.8 billion years, completely consistent with everything we know about stars. Hang on a second, though. You might have heard, and rightly so, that there's a controversy over this. While teams using the cosmic microwave background might all obtain one value for the expansion rate, and teams measuring the large-scale structure of the universe might agree, other methods yield a wildly different value. The other methods, rather than beginning with an early imprinted signal and measuring how it appears today, begin close by and work outward. They measure distances and the apparent recession speeds of various objects, a method generally known as the cosmic distance ladder. When you look at the distance ladder measurements, they all appear to give systematically higher values, between 72 and 76 kilometers SSMPC, about 9% higher on average than the value you get from the cosmic microwave background. You might think then that someone's right and someone's wrong. If the distance ladder team is correct and the cosmic microwave background team is wrong, then perhaps the universe is 9% younger than we think, just 12.8 billion years old. But that's not how it works in practice. The data from the cosmic microwave background isn't something that can just be ignored. It's something that must be reckoned with. The peaks, valleys, and wiggles that we see in its temperature fluctuations are a reflection of all these different parameters combined. Sure, the best fit values are for a universe expanding at 68 kilometers SSMPC and with 68% dark energy, 27% dark matter, and 5% normal matter, but those can be varied, so long as they all vary together. Although it doesn't fit the data quite as well, you can up the expansion rate to, say, 74 kilometers SMPC, and still arrive at a very good fit, so long as you're willing to change the relative fractions of dark matter and dark energy. With a little less dark matter, 20%, and a little more dark energy, 75%, a substantially higher expansion rate can still fit the data well, although not quite as well, as the consensus values. However, what's fascinating about this is that the derived age barely changes at all. If you explore the full range of what is and isn't allowed, that 13.8 billion-year-old figure only comes along with an uncertainty of about 1%, between 13.67 and 13.95 billion years. But it's true that there are still many mysteries left to be uncovered about the universe. We don't know how fast the universe is expanding, and we don't know why different methods of measuring the expansion rate give such wildly different results. We don't know what dark matter or dark energy are, or whether general relativity, from which all this is derived, is still valid on the largest of cosmic scales. We don't even know exactly how much of the universe is locked up in which form of energy. It could have more dark matter and less dark energy than we think, or vice versa. The uncertainties are substantial. Similarly, we know that the universe is approximately 13.8 billion years old, but its exact age is not yet clear. Even today, the matter remains open to discussion, as new research could at any moment upend our previous cosmic conception for the age of the billions of galaxies that comprise our universe. That's what happened recently, when a new study based on James Webb's data was released, challenging the long-held notion that our universe is nearly 13.8 billion years old. If the findings of this latest research prove accurate, the Big Bang may have taken place 26.7 billion years ago, making the actual age of the universe nearly twice as old as we thought. According to Rajendra Gupta, a theoretical physicist at the University of Ottawa who authored the study with the new model, we can explain the conundrum that has long puzzled scientists about these ancient galaxies. That's because Gupta's newly devised model stretches the galaxy formation time by a several billion years. This age estimate is derived from the universe's expansion rate by measuring the redshift of spectral lines in the light emitted by distant galaxies. The redshift of light is what has long helped to inform physicists' estimates of the universe's age. In simple terms, the thought has been that the redshift indicated the distance of stars and galaxies, and hence, the faster they are moving away from Earth. By estimating the rate at which the stars are moving away, scientists can calculate how fast space is expanding into an infinitely growing universe. But the so-called tired light theory that originated in 1929 with Swiss astronomer Fritz Zwicky offered an alternative explanation. Perhaps the redshift we see isn't due to galaxies moving away from us. Instead, Zwicky's hypothesis was that it might be because light loses its energy and shine after traveling a long distance. Gupta proposes that if we allow Zwicky's theory to coexist with the idea of an expanding universe, we can reinterpret the redshift as a hybrid of both of these phenomena and thus arrive at an even more accurate age estimate of the universe. And Gupta goes even further in the study, introducing the fundamental physics idea from English theoretical physicist Paul Dirac, that coupling constants govern the interactions between particles. What does that mean? If these constants evolve, then the time it takes for the early galaxies observed in the Webb telescope to form extends from a few 100 million years to several billion years. Better put, it would offer an explanation for the advanced level of development and mass observed in the previously puzzling early galaxies. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.